Hello everyone, my name is Anthony Shivkumar, and in today's video I will be talking about how to get the GD3000 working. So I basically have got all the necessary boards that could help me test the GD3000 algorithm, and from there once again I can look at the software and understand how the software works. So this is the pre-driver, that's the actual chip, and if you want to test how it works, you can buy the driver over here or the pre-driver, and then you can stack them up to test them out. And you need to buy 3 boards. One is the microcontroller board, you need to buy the GD3000 board, and the power stage board. So what I have over here is the microcontroller board. So you can use the KV31, and I'll show you why we need to use this. This is the GD3000 board, as I mentioned, as we saw in the document over there. So this is the GD3000, and what I'm going to open right now is the power stage board. So this is the power stage board that connects to the brushless DC motor. So that's going to be in this box. So this is the power stage EVB, and let's try to open this. And then here we have, say, what does it tell us? It tells us that there's the power stage board, and then it's a quick start guide for generic analog board. So this is the chip. And let's open it. I've been trying to base my design on these boards. So since I've been having some issues, and I've also blown up one of these boards that I bought, I have basically bought a new one and see whether it works. All right. So the first thing we're going to do is we're going to stack them all together. And here we have it. It's all sandwiched together. So this is the power stage board, and here you have the 6 MOSFETs. This will be connected to the brushless DC motor driver, and here we'll connect the power stage. And these are different types of, this will be the shunt resistor, and then you have a lot of debugging pins all around test points to basically check check, you can connect an oscilloscope and see if the waveforms are right. So there's a lot of debug capabilities throughout the board, including on the GD3000 over here. Quite a lot of debug capabilities all throughout the board. And then here we have the KV31. So this is the NXP power stage board, and now let's see how it let's get it working. Okay, so the power stage board is over here. Where do I have it? So this is the GD3000, and once you go to the power stage board, let's figure out how we can download the code. Go to product summary, and now that we have over here, so what you can do is go to the embedded application GD3000 software, and once you download it, you should be able to get into a folder that is called the three-phase SDK. It'll be something called as the TPP SDK SWs, which basically means the three-phase pre-driver, software development kit, the software. And then here you have the KDS example, which is the Kinetic Design Studio. And the one that we're going to test is over the KV31 BLDC control. And in here, you have the KV31. That's the reason why we're using the KV31. So this particular breakout board, can power a lot of other Freedom boards, especially when it comes to motor controllers. So the KV31 is a very important board in the Freedom ecosystem of NXP. And that's what we're trying to do. We're trying to set it up the way we have it right now. So we have the Freedom board, and we'll try to set up the power shortly. And these are all the connections. By default, while you sandwich it together, the connections will automatically be the right pins will be connected to the right pins of each board. So if you follow the instructions, so what I've done is basically downloaded the Kinetic Studio, and then I basically imported by following the instructions. And once you import it, there'll be a folder structure called the three-phase TPP, the three-phase pre-driver Freedom KV31 BLDC controller. And this basically will have the code that can configure the GD3000 as well as the, make the motor work. So what we have over here, this is a template for main module for the Kinetic Studio. And we'll go to the code shortly, but let's get it working right now. So what I'm going to do is I'm going to build this. Now there's a thing where I need to basically download code. So what I'll do is go to the McuXpresso. And in an McuXpresso, I can download the code over here. So what I'm going to do is I'm going to connect my USB driver. And as you can see, it will basically show that the KV31 is connected. And right now it's running a different code. So let's try to install the code that we want. So if I click search again, it's basically found the code, found the driver. So we'll click open, and then let me go to the workspace. So I might have it already over here. If not, then I can go to the file system. And in here, it would be under the NXP Freedom GD3000, KDS example, the KV31 BLDC control. We'll go to the release code, and in here we can basically click everything, and here we can download the ELF code. All right. So I'm going to basically click here and click open, and in here I am just going to click run. So before we do that, we'll look at the thing and we'll see if this flashes as soon as I click. What I'm going to do is basically add the. I'm just going to go to my. Put this as camera 4 on. Let me just put this on. So yeah. So now what we're going to do is I'm going to click run, and we should see this basically downloading some code over here. So I'll just center this a little bit so we can see this properly. And there you go. It's flashing. And then the code is already downloaded. Perfect. So now we have the code downloaded. And now let's try to basically get it to work. So I need to connect my power source. I'm going to install this to see what we're going to connect. So this is a 2S pre-driver or motor, brushless DC motors. So I require around 8 volts to basically power this. And I think I can I would use my, I can use a battery like this to power it, or I could even use my voltage source over here to power it. So let me try to use my battery to power it, and let's see how it works from here. So this can get a little tricky because of the way this connection is done, but we'll try to figure this out. So over here, this is the positive, and then based on the way this connection works, so positive, positive, and here this will be positive. So this will be and this should be negative because the back is going over here, so this is negative. It's just the way this damn thing is built. Sad but true. And so I'm just going to disconnect the battery because and I'm also going to disconnect actually I don't need to disconnect this. It gets a little finicky in that sense. I'm going to connect the three motor pins. That's one. That's two. And we have the third one. And that's three. All right, and now I should, this has come out. Yeah, these connections are not the best in my opinion. I am going to put them onto a board. Just elevate this a little bit. So we're a little close by. I'm going to put the probes on to check the voltage before we connect everything. So this should be positive, and here we should have negative. And that's positive, that's negative. All the connections are now running. And now let's connect the power source. So we can see it shows 7.8 volts. That's coming from the battery. And I am going to now okay, so it did spin, and so that's technically working. And I'm a little scared because I've been blowing up a lot of these things, so I do know the code should work, but we'll the thing with these boards do not have a protection mechanism. It does have a protection mechanism, but the software the default software doesn't enable the protection, such as over voltage or over current. So as a result, there's no way to stop it. So but what I can do is I'm going to bring my thermal camera as well, and we'll try to basically see how much heat that is producing over the MOSFETs, and if anything is getting heated, we would know. And here is basically what I will do, just to keep things a little clearer. I'm just going to spin this a little bit over here so we have a little bit more space. Here is basically the thermal camera, and right now everything is basically room temperature. That's around 29 degrees. It all looks good to me. All right, and I'm just going to start this damn thing on, and now let's see how it works. And you can see how hot the MOSFET is getting. Look at that, that's 34 degrees. Yeah, so you can see how hot this is getting, 41, 40, and now it's really hot. Like, this is what this board is doing. Like, it's these MOSFETs. And one of the reasons why these things are blowing up is because the amount of current these things take. Like, let's see how hot look at this. So right now the motor, the windings in the motor is around, let me try to plan this over here. So around 40, 42 degrees. So the motor itself is getting hot, the wire is getting hot. But look at the MOSFET. The MOSFET goes to approximately, when it was running, it was at almost 70 degrees, 80 degrees. That's a lot of heat. So you can see that while these MOSFETs are switching, it's consuming a lot of heat. So that's the reason why I've been blowing them up, because I didn't realize that they produce so much heat. And if it's not, you don't have a thermals protection, right? Or if you don't have a protection mechanism, it can blow up. So yeah, as you can see, it is spinning properly with the GD3000. I don't know how long I can make this spin. I don't want to blow the second piece of my hardware, but I can see why they blow up. That's how much heat they generate. So we'll try them again. And this is basically the green button, and then we'll go through the code. So look at how hot it gets. So right now the average is 33 degrees. Look at this over here. So this temperature over here is telling me that this board, that where we're pointing at, around here, is around 33 degrees. And this is the range. The range is from 24 degrees to 36 degrees. This is basically the gradient range, just to give us an indication. But this is the actual temperature right over here. Okay, and now let's do it over here. So we're around 8 volts. That's the power that's coming over here. That's around 2S. And this motor can handle around 2S. It's pretty okay right now. Like, as I mentioned, it's around 34. It's around room temperature. So is the board is around room temperature, approximately room temperature. And now let's do it again. So now look how hot it gets. Look how hot it gets. 70 degrees, 74. Wow. And now let's see how hot the motor is. Even the motor is around 46 degrees, 56 degrees. No, the windings of the motor are so hot. Look at that. And now it's coming down because I've stopped it. So if I continue right now, you can see how hot even the motor gets. Look at that, the motor. Look how hot it's getting. Look at this. Yeah. All right, so this is what I wanted to show you. It's that, like, when you're dealing with electromagnetics, when you're dealing with motor construction, the brushless DC motor, the pre-driver, they all go hand in hand. Like, you can't, I mean, I know when you do hobby work, it kind of, you basically can plug and play and get anything to work. But when you're designing the whole system, especially for, say, this quadcopter, you can realize that there's thermal capabilities that you need to account for, not to mention that there's the software capabilities as well. There's a lot of parameters that we want to take care of when we're designing these boards, and it gets a little complicated if you don't consider these factors, especially thermal. There's always going to be I²R losses, and that heat that this is generating is I²R losses. They're switching frequency in the switching losses, and it generates a lot. I mean, I could boil water. It is going to 100 degrees Celsius. So let's look at the code and have a look at what's really happening. So in here, and another reason why you need to know is because if I put in a different motor, which I've been blowing up, I've been using a 3S motor on this. Yeah, this is hot. When I was using a 3S motor on this, that means and I was powering it by 8 volts. This was drawing in a lot more current, and as a result, this was drawing so much current that it just blew up these MOSFETs. So I can't use any type of motor with any type of voltage. You have to have everything in sync, because the voltage will still power any motor, but you want to make sure that you're powering the motor with the voltage that is recommended. Otherwise, it'll draw a lot more current and to have the same power. And if it draws a lot more current, and if your MOSFET cannot handle that current, it will blow up, and that's what's been happening. So yeah, so as I can tell you that this is a 2S motor, which means it can work on 7.8 volts. So as we see over here, 7.9. This is a fully charged battery, or a pretty good charged battery. But if I use a high capacity motor and I power it with a 7S, with a 2S, which is a 7.4 volt, it will blow up. So I need to power it with a 3S, which will be around 11.4 volts or so. So I need a bigger battery if I want to power a bigger motor, because then it won't draw as much current to deliver the same amount of power. So those are the kind of things I've been learning over basically, if you keep blowing things up, you'll eventually learn what's happening. All right, so now what we have over here is the code. And as I mentioned, like, this is very similar to the previous code. What we have over here is the speed simulation, board initialization, the motor initialize the peripheral motor driver. So we're initializing motor M1. Here we have the CPU load measurement, enable global interrupt. And here we have the free master pole. Here we have the ADC interrupt, the fast timer 1, which will be taking care of the commutation. Then you have the fast timer 2, which will probably be taking care of the state machine. And then one slow application machine function reloads the interrupt service routine, call 1 millisecond period, and processes following function. So it processes the motor M1 slow application machine function. Not too sure what exactly this is. I'll have to go to the code. And then you have the demo speed stimulation, and you're okay. I get it. So this particular interrupt is doing this very similar thing where you constantly try to increase the speed or decrease the speed accordingly. Wait a minute. I think I'm going through the wrong. I'm going through the wrong code. Sorry, I was going through a code that also powers the the same drive, same motor, same board, but a different configuration. This is the code for the GD3000, the FRDM-KV31 BLDC. This is the initialization. That's what I was wondering. I was like, wait, this doesn't look right. So this is the 3-phase motor control commutation initialization handler. I'm just trying to explain to you what these definitions mean. So this is a 3-phase motor controller PWM initializer. So when we go to the main function over here, we are initializing the commutation sequence. This is the board initialization pin, the debug console. Now this is not written by me. This is written by the manufacturer. This is a demo application, but it's always good to understand what's going on. So here they're basically configuring the fast timer or the flex timer 1. Here we have the GD3000 configuration. So it's setting the GD3000 configuration over here. It's setting this SPI configuration, the 3-phase device configuration. So this is all initialization basically. And here we have the speed. So if direction change, if it's running, you can basically set the direction to different directions if you want. We could even do that. And then here it's if it's running, you can set the direction. If it's, or you can, I mean, this is basically a simple if else statement based on what the state of the motor is. If it's running, then you stop it and then you change it. And if it's already stopped, then you just change it, something of that sort. And here you have the and let's look at the 3-phase run. I believe one of this should be the speed. Set speed. If not this one, then it should be set torque. No, that's not where we want to go. Just trying to get to where the speed is. This where the speed is? So if the driver speed is equals to speed, okay. Oh yeah, we can set speed 1. No, yeah. So the final speed for acceleration and RPM. So here I've got speed 1 and speed 2 at 3000 RPM. So it's very, very fast. I don't think this is the default. I think I've changed this value. So it's basically always going to run at 3000 RPM. What I will be doing next is to really get a sense of what's really happening. I will try to put in debug probes everywhere. So let me just disconnect everything. I don't want to load this application again. So as you can see in here, we have different test pins. I'll try to put different test pins around here, connect it to the oscilloscope, and then see what's really happening, what's happening physically while the motor is running. And I think that'll be a good insight as to what's really happening in a brushless DC motor driver. And then we'll start to design our own brushless DC motor driver for the bicopter or the drone that we're creating. All right, so that's all there is from me today. If this interests you, please like and subscribe. And until next time, take care.